Good evening and welcome to my discussion on budget deadline constrained workflow planning for admission control with a focus on the BHEFT algorithm. So why do we need budget planning? In grid or cloud computing, resources provide various services at various prices. The users may require workflow applications to complete within a certain deadline or budget. This is better known as quality of service. So how can we ensure that quality of service is enforced? We do this by putting a service level agreement in place. This is an agreement between the service provider to capture the quality of service desired by the user. So we've talked about HEFT before, and we've seen it presented in the class. So why not just use the HEFT algorithm? The earliest finish time sounds like it would fit our needs just fine. The primary goal is to execute a workflow in the fastest time. However, HEFT does not take budget into consideration. HEFT also does not take existing resource reservations into consideration. So let's talk about budget constrained plans, or BDCs. Below we have a diagram of how these work, and let's quickly run through them. So a user communicates with the resource planner. The planner sends a time service query, or TSQ, to the local resource manager. The local resource manager checks existing loads, and he will send the query back to the planner, letting them know if it is possible to accept the user's request or they have to reject it based on the time service query. And again, we can see in the picture below just how that works with the steps. So what are some of the challenges in the paper that we found with BDC planning? Again, many do not take into consideration existing loads. We cannot have overlapping reservations, as we can only have one task running on a resource at a time in this environment. And some BDC plans, as discussed in the paper, are not cost effective. So let's break down the BDC plan here. The first in our first chart, chart A, is an example of a DAG, which they refer to in the paper, directed acyclic graph. And you can see we start at task 0, and then we move through the various tasks, and they have the amount of data that's moving through each task and the dependencies that they have. In figure 3b, we can see the estimated execution times for a task on each resource. In 3c, we can see the time to transmit data units on the three various resources. In 3D, we see the price of the three various resources, and then we can see the existing loads over there in 3E that we have on each resource. So let's talk about BHEFT heuristic, or better known as the BHEFT algorithm. BHEFT is a proposed modification to the HEFT algorithm, which is focused on the earliest finish time. And what we're going to do is look at the steps that they have put together for the BHEFT algorithm. So DAG G with budget B and deadline B is our input, and our output is a budget deadline constrained plan. So first we're going to compute the rank as defined in equation 1, which is pretty simple. We're going to sort all the tasks based on the rank in non-ascending order. For all of the tasks that we count, we're going to select the kth task from the planning list, and then we're going to compute the spare application budget. And that is just summing up and taking away, starting at the task K and all the way through N, which is our last task. Computing the current task budget is going to be CK bar plus spare application budget K times AFK. And from there, we'll be able to put together a affordable services list, as we can see in equation 5. and then we can move into the selection portion of the algorithm, which selects the best possible service with the rules as follows. So if SK is equal to 0, then the affordable task or the affordable service with the earliest finish time is selected. If we have spare application budget that is greater than 0, then that is less than 0, then the service with the earliest finish time is selected. If spare application budget is greater than 0, then the service with the earliest finish time is selected. If we do not have the spare application budget, then we will select the cheapest service. After we make the best possible selection, we compute the earliest finish time in mapping task KA with the service using TSQ, as we saw in the earlier selections. So let's take another look at the BHEFT in more of a detailed illustration. So in Table 1 we can see all the computations, the rank, the spare application budget, the current task budget, AFK, which is the ratio, the list that we have available for each task and what resource it can run on, the selected task, the start time, the finish time, and the cost. So as we run through this list, and we can see on the bottom, I brought back the prices because that is relevant to this discussion. Most of our, considering that this is the budget constraints, most of our tasks are going to be run on resource 1. So starting with task 0, which is run on resource 1, we do have the option of running task 1 on resource 1 or 2, and then we also, but we are selecting 2 in this case, then we move to 4, and then task 2 and 3, and then we have a dependency with task 7, 5, and 6 running, and then we have the spare application budget to run task 8 on resource 0, which is our most expensive resource, and we need to get that completed because we have a dependency to run task 9 and get it within the deadline, and also taking into consideration the existing resources. So in the paper, we discussed some other budget deadline criteria, and the one that was probably the most serious competitor with the BHEFT algorithm is the loss planning. And the way that the loss was explained is that if the cost of an assignment exceeds the budget, then the loss routine is invoked. The loss weight is calculated as T new minus T old over C old minus C new. So let's put the BHEFT algorithm to the test, and we saw this in the paper, but we needed a metric to be able to measure how well BHEFT was doing against the other BDCs. So they put together this metric called PSR, which is the performance rate, and it's the number of times that a BDC plan was found divided by the number of times that an experiment was repeated. So in the first experiment, we wanted to keep everything equal as far as the budget and the deadline are concerned. So they were locked in at 0.5, and you can see the planning success rate on the left-hand side, and we have all 4 of our BDCs listed here, and then we move through various amounts of utilization rates, and you can see BHEFT on the 53 node system does exceptionally well, but you can see as we move through and the resources do become more scarce, that we see a drop in performance, especially at 0.4. This is also true on the 77 node system. More of the same. BHEFT looks to be outperforming the other 3, especially with the lower utilization rates. as we move through to our 98 node system and our 124 node system, we can see that once the utilization hits 0.4, all 4 of the planning heuristics absolutely disappear. In experiment 2, we take the utilization rate out of the equation, but we do start to change up our deadline and our budget. And you can see we have various combinations of the deadline and budget, and as we move through, BHEFT still does exceptionally well against the other BDCs, especially as we start to loosen the constraints and move towards a 0.75 budget and 0.75 deadline. And continuing on with experiment 2 with the 98 node system and 124 node system, more of the same, where the BHEFT algorithm is outperforming the loss TSQ, BDLS TSQ, and the DCA. We do see that loss does actually start to outperform the BHEFT algorithm with the constraints being loosened on these higher node systems. So in experiment 3, we bring utilization rate back into the equation. In the first one, we see utilization rate at 0.2, and we're also looking at the mixture of budget and deadline. And still, we can see that the BHEFT algorithm is very well performing against the other 3 BDCs. We do see as utilization rate increases with the tight constraints, all 4 of the BDCs do run into trouble, and you can see their planning success rate is reflective of that. So still in the 98 node system, but we're just looking at the 0.4 utilization rate. It is almost non-existent it is non-existent in the first 3 combinations of budget and deadline, and we start to see it pick back up in the 4th with 0.5 deadline and a 0.25 budget. And then once we loosen the constraints up almost completely, we can see BHEFT algorithm competing well, but still having a little bit of trouble against the DC or the loss and the BDLS. On a little bit smaller system, we still have the same deal, utilization rate of 0.2 and going up to 0.4, and we can see the BHEFT algorithm performs well on these smaller systems, and then as the utilization rate gets to 0.4, again we see almost non-existent in the very tightly constrained 0.25 budget and 0.25 deadline. They do start to loosen the budget a little bit with 0.5 and 0.25, but there's still no planning success rate at that level. So how can we rank the BDC plans after looking at these experiments? So we have AR, and the AR is computed by how they ranked, and each time they achieve the rank 1, 2, 3, or 4, and the formula is R1 plus 2R2 plus 3R3 plus 4R4 divided by 100. And as you can see, the BHEFT algorithm had 1.71 AR, which is the best score, but not far behind it would be the loss heuristic. BDLS is a pretty close second to the loss, and then DCA was the least effective, coming in 4th and 3rd the most. So here's some final thoughts. Existing loads may degrade PSR for most of the planning heuristics, but the BHEFT algorithm does take into account existing resource load and is able to achieve significant improvement on PSR. There were times where the loss was invoked and it was able to outperform BHEFT, but this is at a much higher cost, and considering that this paper is looking at budget constraints, BHEFT algorithm would still be a better choice. In addition, BHEFT is also a good choice for scalability. Thank you very much.